to us about private information retrieval.
Thank you very much, Henry. Thanks for the invitation. Really nice to be here. So, as said, I'm Camilla from Aalto University, and I'm going to walk you through a story where we try to really close some, I would say, quite basic capacity results in private information retrieval. It turned out to be quite difficult. So first I will introduce you to the basic problem of PIR, private information retrieval. Then I tell you what we know about the capacity results, and then I tell you what our conjecture is or was. Now this is maybe not a good way to write, but it's approximately a theorem nowadays. And how we got to that requires me to explain our star product PIR scheme, which is a very kind of maybe universal way of doing PIR. And then we need to refine that even a bit further, so then we get to this kind of a technical, but in a way very natural full support rank criterion for our schemes. And in the end, some current and future extensions of these works. And it's a collaboration with many, many people. I won't spend half the talk telling about their lives, but you can maybe recognize some of them. Most of the things that I'm going to talk about today are done with Ragnar, who is here, and Dave, and Oliver, and Razan, and Salim is here. Just a small picture, because I mean, in the end, maybe, so I think we have 1 or 2 papers together on PIR, but he's actually very important because I got interested in this problem when I was visiting Salim already, I think, almost 10 years ago in Chicago, and that got us doing this, all this stuff. Okay, so what is private information retrieval? Probably many of you know. So our task is to download 1 out of some M files from a database, or more generally from a cloud or distributed data storage systems. And we don't want to reveal the identity of the file. And now these are not powers of X, these are superscripts indicating the file index. So say I want to retrieve the first file, I don't want the servers or the database owner know what this index was that I was interested in. So the data as such is not secret. So it could be like Netflix movies. I just don't want Netflix to know which movie I was interested in, but everybody knows what movies there are. And we know also information theoretically that if we only have 1 server, or equivalently, if all the servers are colluding, then we cannot achieve perfect privacy unless we download actually the entire data. And this is very infeasible when we have a lot of data nowadays. So what do? We distribute the data over some N servers, and then we can either do it in a replicated manner, or we can do something smarter using, for instance, NK MDS code. Also, by the way, please interrupt at any point if you have any questions. And this is a very short and ignorant and lacking history of PIR. So it started in 1995 by Cho et al. So mainly like a question, how do I retrieve single bit from an M-bit database? And then there was a sequence of papers reducing this communication cost to be sublinear in M, and M was the number of files. And while sublinear may sound impressive, but if you think of modern data storage systems or big databases, then M is a very large, potentially very large number, so it's still maybe not such a great thing. So then more recently, there was kind of a renewed interest from this more coding theory point of view, because we had a lot of work on distributed data storage systems, coding for such systems and so on. So then kind of thinking that, okay, if we now consider such systems instead of a database consisting of a string of bits, then what can we do? And there we suddenly get into kind of very interesting questions, in a sense that we can assume that our files are, first of all, very large. So the query size kind of becomes negligible. So the query size is proportional to the number of files. But suddenly now we can ignore it because it's much smaller than the size of our modern media files, for instance. So there was renewed interest from this point of view, and there were few works, let's say, soon after 2010. And then there was kind of maybe even, let's say, third wave of works that started looking at these things from a capacity point of view, and with this ignoring the upload cost part. And just out of curiosity, I was checking on IEEE Explore how many hits I had when searching for private information retrieval. And of course, it's not all the works in private information retrieval. But I think it's interesting because this early decade gives only 7 hits. Of course, many more works were out there, but it probably reflects the fact that it was mainly a computer science, more algorithmics community maybe in the early days, and then coding theory started stepping in. We got more and more IT society people or math people coming to the play. And then there's a clear increase during the past decade. And it's not all ours, so some other people got also. So let me start by a very simple toy example. So we have a simple parity check code with 3 nodes and 2 information symbols. So I encode my 2 information symbols into 3 data symbols, and then I put each coordinate of my code word on a respective server. So these boxes are nodes or servers. So each row here is an encoded code word. So if I have my first file, so x1, the superscript is the file index. I first split my file into 2 information pieces. I store them on server 1 and 2 respectively, and then I store their parity or their sum on the 3rd server. And more generally, whichever code word you have, you put 1 coordinate on each of the n servers if you have length n code. And now this is a silly example. I only have 3 files. So the superscript is the file index, and the lower subscript is the server index. So if I denote these by y's, I form them by some linear code. So I have a k by n generator matrix, and then I take the jth coordinate yj, and I store it on the jth server. So just to recall the parameters, k is the number of information symbols, n is the length of the code, also the number of servers in the system, and subscript here is q. Now I'm just doing binary. And then n is the number of servers, and m is the number of files that I already said. Repetition code. So what do we do then? So we want to retrieve the first file, but we don't want these servers to know that we were interested in the first file. So first we choose random vector, let it be 101. The length of this vector is m. Now both n and m happen to be 3, but the length of this one is m. So you can think of it as a column vector rather than a row vector. So the length matches the length of the data on each server. So then I'm sending queries, and these are just basically this random vector that I've selected, except now that I'm interested in the first file. So let me first try to get this first piece on the first server. So to the query that I sent to the first server, I simply flip the first bit. So I add the first standard basis vector to my random vector. And to the other servers, I'm sending just a plain random vector. Then what the servers do, they simply project their data on my query. So in other words, they take the inner product with the data they hold with the query vector. And they send me that inner product as a response. And then I can decode my desired file piece from these responses. And now that I'm binary, I can just XOR all these responses together, and I'm going to get my first piece of the file that I wanted. Okay, then I'm still missing the second piece, which is now lying on the second server. So I do a second round. I choose a new random vector. I do exactly the same thing, except that now I want the piece from the second server. So I'm flipping the first bit to the second query. So I'm adding E1 because I'm interested in the first file, but I add it to the second query because I want it from the second server who is holding the respective piece. And again, same process. They project their data on my query vectors, and then I can just XOR or do some other linear function in a more general case with some q larger than 2. And now why is this private? It isn't unless I make this assumption that these servers don't talk to each other. So of course, if they tell each other what kind of queries they got, they can get exactly the same information as the user requesting the file has. But if I assume that they don't talk to each other, they are just getting a random vector. They have no way of knowing if there was some bit flipped or not. So privacy holds if there is no collusion. So we call it collusion when they might exchange their queries. Any questions at this point? No. All right, so then what about collusion? If some of them actually do exchange their queries, then what can I do? So I can still do this. Let me first give a more formal definition about it. So we say that the scheme protects against colluding set J if, when we project the overall query, so if you look at together all the query vectors that I sent to the system, and I project it to the columns that correspond to the colluding servers, then what I see should not depend on the file index. So there should be no difference whether I'm looking at this for the interesting file or some other file. You can formulate all of these things in information theoretic terms, of course, as well, but I keep it casual for this. And then we say that we have a TPIR scheme if we can protect against any colluding set of size at most T. So T is the collusion parameter throughout the talk. And so how do we measure the goodness of such a PIR scheme? So we talk about rate, and what is the rate? So we want some file, so we divide the file size, so the kind of number of desired symbols that we want to download, by the total download size. So of course, if we don't care about privacy, then we just ask for the file, so this ratio would be 1. But then if we want to add privacy, we need to add some redundancy or interference there to confuse the servers, then I need to download a bit more. So this is always less than or equal to 1. And the capacity is then the maximum of all those rates given some setting. And we say that the scheme is asymptotically capacity achieving if the rate is the limit when the number of files goes to infinity. And what do we know? So we know many things. So if we just replicate the files over n servers, then the capacity is known and we know how to achieve it. Same with MDS coded storage and same with colluding servers. So then one might jump to conclusion, like we also maybe thought in the beginning, that combining MDS and colluding should not be too hard. You take this from there and that from there and you're done. But that was not quite how it ended up working. And that's mainly what I'm going to talk about today. So in addition, there's a bunch of more settings being considered, but I will not spend time on those because it's a short talk. So just to summarize and give you the exact figures. So remember, n was the length of the code. K is our number of information symbols. So here, if we have replication, we have n1 code. T is the collusion parameter. So here, if we are not doing anything but replicating, we can approach to 1 if we just keep adding servers. If we do coding, then we have this K penalty here. So the higher code rate, then the worse the PIR rate. So there's kind of a trade-off with storage overhead and the retrieval rate. Collusion gives a similar penalty. So if you want to protect against any T colluding servers, then we have such an expression asymptotically. And if we combine these, as I said, this turned out to be difficult. It's still not fully resolved, but we have mostly resolved it. But so we made this as a conjecture in our 2017 paper. And then Saeed Jafar and his group, they came up with the counterexample in the case of 2 files. So if there are 2 files, you can do better than what our conjecture would predict. However, it turned out to be very difficult to generalize that counterexample, and then we started thinking in more detail, like, why is that and what's going on here? So we'll give you more details about this. So in this magenta, now the colors are hidden a bit. Can I get rid of this thing? No, I can't, sorry.
For the NK coded case, that's like this MDS type straggler. Like you get just any K pieces for them, right?
Mm-hmm. Yeah. Yes. So these, as said, we made this conjecture 2017, or 16 was the first version. Then a year later, or a bit more later, Sun and Jafar came up with this counterexample for 2 files. And then in the magenta paper, quite a bit later, we managed to prove this under this so-called full support rank technical assumption that I will tell you more about in a minute. And now if you just look at this, so maybe especially communications people are used to thinking that, okay, these asymptotic scenarios where you need some infinite length codes, these are not practical, or okay, maybe nowadays they can even be made practical. But anyway, here, the asymptotics are with respect to the number of files. And it decays these expressions, finite number of file expressions decay exponentially in M So we are actually approaching the asymptotic regime with very small number of files. So here, kind of the practical setting is the asymptotic setting, something to just keep in mind. So one could say that being a bit obsessed about proving this is mainly for the sake of theory and curiosity, not so much for any practical purpose. And here, picture about what I just said. So this is a case where we have coding, no collusion. And if you look at this finite file expression and then the asymptotic one, we are maybe around 10 files, and we are already asymptotic, essentially. And same holds if we add collusion and so on. So then maybe just to give an idea how one goes about proving such capacity results. So this is maybe familiar to folks here, but you would first make some information theoretic argument to get some upper bound, and then you would find some concrete scheme that achieves your bound. And then you have a capacity achieving scheme. So let's look at the simple case of just replication. And the claim is that the rate is upper bounded by this geometric sum or its inverse. So in other words, by this expression that I showed on the previous slide, and asymptotically, then of course we would approach this expression here. So now if I first give you a sketch of a scheme that can achieve this claimed capacity bound, and then we can look at the converse proof a bit. So let me just give a toy example, but it will generalize to any parameters. So I have two files, A and B. I store them by replication on two servers. And I need to now sub-packetize these files, so stripe, or whatever your favorite word for splitting up the files into smaller pieces, into 4 symbols. 4 is not that many, but what 4 really is here is n to the m, and m was the number of files. So this is really, again, for proving something theoretical rather than a scheme that you would ever use in practice. I will also give you a but more practical scheme in a minute. But for now, we split this into exponentially many stripes, and assume now that the user wants the first file, so they need to download these 4 symbols of A, file A. And now my strategy is as follows. So first I will download, I will query so that I get A1 from the first server. Then due to privacy, I need to symmetrize over different servers, over files. Then I'm going to ask for something kind of redundant. So I'm going to use these pieces of B as interference so that I can then make some suitable linear combinations and get what I want. And turns out that by making these splits, and then in the end, of course, I don't do this in such a chronological order, but I would randomize. So what I'm now doing is that in order to get these 4 pieces of A, I'm downloading 6 pieces in total, so my rate is 2/3. And maybe you don't compute geometric sums in your head so quickly, but it happens to match with this expression here, and you can generalize this example very easily. So then how do we know that this is the best we can achieve? We need some information theoretic arguments, and I'm hiding all the information theory and entropies and mutual informations here. I'm just giving like an intuition level sketch of the induction proof. So I'm claiming that the number of symbols that I'm downloading divided by the number of symbols in the file that I actually want is at least this geometric sum. Now I swap the numerator and the denominator because I had the -1 in the exponent. And now if we denote shortly the file size, so the desired symbols, number of desired symbols by L, then I'm claiming that I need to download at least this many symbols. I'm just multiplying by L both sides. And so if we just have one file, then it's very clear. I need to download at least the L symbols that are in the file that I actually want. Then I make an induction assumption for M files. So then we, by our induction assumption, need to download dm symbols, which was this expression here. And in particular, what this means is that because I have n servers, then from some server, I need to download at least nth of this dm number of symbols. And now for the induction step, assume I want m plus first file. And what do I do then? So by induction assumption, I need dm over n from some server, from the files 1 to m. And now if I want the m plus first file, then I need to, of course, download still the L symbols in that file, because those are the symbols that I want. So in total, I need to download at least L plus this, what I got from my induction hypothesis, and this happens to be D m plus 1, and it proves my induction step. For real, you, of course, you need to consider some entropies and be a bit more careful here. And so if you would look at the similar proofs for coded storage or for the colluding case, they are very, very similar. You just utilize the fact that for the coded case, any k symbols are linearly independent. And for the colluding case, you have t linearly independent things as well, because otherwise they could figure out something from the symbols the colluding set sees. So then the question is, can we just simply combine somehow these proofs to get coded and colluding case? But as I already mentioned, this turned out to be not so straightforward. So this conjecture is repeated here. So you saw it already in the capacity table. So we are saying that if we have an NKD code, M files, and T is between 1 and n minus k, just for the sake to have a non-negative rate, then any TPIR scheme has rate at most this expression that would be kind of maybe your natural guess based on the other results. And asymptotically, it would be this expression here. And so we didn't just pull this out of our hats because seeing the earlier results, but we managed to build a nice scheme that gets to this asymptotic conjectured capacity. So then we thought that it's natural to extend this claim to the finite verse. And a little bit of repetition, but let's see what happened in a bit more detail. So there was a counterexample with 2 files, and K and T, so the coding and the collusion parameters were also 2 and 4 servers. And they managed to get slightly higher PIR rate with their counterexample than what our conjecture would have claimed. So for M files with no further kind of assumptions in our conjecture, it does not hold. Then, of course, 2 files is maybe not such an interesting case because you can just download everything and you are private anyway. So how did they manage to do this is that this query scheme that they have in the counterexample is not full support rank. I didn't yet tell you what full support rank means, but I will do so in a minute. So that kind of prompted us after some work when we understood what's really going on in their counterexample, made us to add this technical assumption in our conjecture, and then we were able to prove this conjecture. Okay, so let's look at now how did we do it and what is this full support rank? How am I doing on time?
Say probably about 5 minutes.
5 minutes? Okay, perfect. So then I need to tell you first what is our star product PIR scheme. So we already heard about star products of codes earlier, so that's exactly what we are doing. So star product, just the coordinate-wise product, and then the product of star product of codes is just the linear span of all of those. And we know also that we have something similar to the singleton bound, namely the product singleton bound. And we know also that if we want to get to this upper bound, we can only consider some trivial pairs or generalized Reed-Solomon codes. So we propose this, I would like to say, fully general coded retrieval scheme that can protect against decollusion by utilizing this star product way of looking at things. And asymptotically, this scheme achieves all the known points where we have actually proved capacity expressions when we use the GRS, generalized Reed-Solomon codes. And it also achieves the asymptotic capacity of the previous conjecture. And so what was kind of very nice and maybe novel in this way of looking at things is that if you remember still the toy example that I showed, what happens there is that you choose n queries, 1 per each server, and you choose them from the entire space. When you choose this randomness, you use the entire space fq to the m. So whereas now when we look at these as star products of codes, so we have some storage code C, and then we consider actually now a retrieval code D. So instead of looking at our queries as these long columns, m-length columns coming from fq to the m for each of the servers, we now choose length n short code words corresponding to the number of servers from this code D. And then we stack them into our query matrices. So each of our column in the query now includes 1 coordinate of each of these code words. So we are kind of looking at our query, whole big query matrix row-wise instead of picking things column-wise as we did earlier. And now the dimension t here in the code D is not by coincidence T, but it kind of controls what kind of collusion we can protect against. And earlier we didn't really have control over this by just picking up random queries. You had to either somehow handpick what you do or have some kind of an ad hoc construction. So now what we see is that what we're getting as responses from the servers is, after looking at these inner products and reorganizing them a bit, what we see is actually a code word in C*D plus something that came from this, something similar to the first standard basis vector when we wanted first file to flip our bit suitably. So we see something in addition to this, and this is something we don't care about. This is kind of all the interference because this was the randomness that we use for the queries. So now that it's actually a code, we can simply project this part off by using the parity check matrix, and we are left exactly what's interesting to us. And what is interesting to us is hidden in this kind of carefully chosen error. And we know the positions because we chose the error, namely the standard basis vector or something similar. So we can consider these errors as erasers. And because we have a code, then we can correct up to d-1 erasers, as we very well know. And now from the product singleton bound, we know that we can at most achieve this kind of minimum distance. And now plugging in the parameters for the dimensions of C and D, we get that we can get a rate n minus k minus t plus 1 over n, which is our asymptotic conjecture. And so now, let me not repeat this, getting to the full support rank PIR. So then, now we only got to the asymptotic version of this conjecture, how to get to the finite file version of this conjecture. Studying the counterexample and studying the existing capacity achieving schemes, we realized that the property we are kind of lacking when the conjecture fails is this full support rank. So it is of course suboptimal to send linearly dependent queries to different servers because we would get same things over and over. However, if you look at the big query matrix, it may have some submatrices that are actually having some dependencies, like they do in this counterexample. So that caused us to make this technical assumption restricting this. So if we look at any at most t size set of columns, t was the collusion parameter, then we force them to be independent. In the more technical terms, if you look at any, you can ignore alpha and beta, but if you look at any support on some t columns, then we want the rank of that submatrix to be equal to the size of this support. So we don't allow dependencies among columns that are supported. And so now, by having added this technical assumption of full support rank into our conjecture, now we are able to prove it, so it becomes a theorem. It's not a completely general theorem, but it is very natural that, in a sense, that it is only this counterexample that does not fulfill this condition, and all the known capacity achieving schemes do fulfill this condition, including our star product scheme and so on. And how it is proven, I don't have time to go into the details, but the converse follows kind of a similar proof that was given in a symmetric PIR case by Mikael Skoglund and Given Wang. And then a capacity achieving scheme can be constructed by using our star product scheme and then so-called lifting and refinement that was proposed by Rafael and Salim. And so how do we interpret this is, like I said, this condition full support rank, it captures kind of this linear independency of the queries that most of these schemes have in common. So in other words, if you want to really exceed this finite file conjectured capacity when talking about it in full generality, what it requires is that some restrictions of the queries to some T subsets of servers need to be linearly dependent. And this is kind of a tricky thing, like how do you choose these dependencies then? So I invite you to try to have a general scheme that's not full support rank and works for all parameters and beats the conjectured rate. I don't think you can do it. Okay, this I already said. So just to conclude, I've told you about our star product scheme, which is, I mean, the star product in a way is not new because that's in a way what it was all the time. It was just that you didn't utilize it. Instead of having some nice query code, you just had the whole space and you did something in order to pick the queries. But now putting the nice code structure there allows this nice interplay between the storage and the queries. We had some overview of capacity results. I didn't mention the word strongly linear, but it's something that our scheme satisfies, and we can show that no strongly linear scheme can do better than our scheme. And why it is a nice concept is that it allows you to do very small sub-packetization. So if you remember in the toy scheme for the replication capacity achieving scheme, you had n to the m sub-packets. We need something like k times n minus k, and k and n are small parameters. So we have like k squared where k is small instead of n to the m where m is large. Also, this scheme is highly generalizable. So we've been working with stragglers, adversaries, over networks, streaming, distributed computation, interference alignment, quantum, you name it. Okay, so then what are we doing currently and what next? So here are some more pictures. So Okko has been working on this secure distributed matrix multiplication, both over finite fields and over the analog domain. And then we have, which is not our work, are these very nice cross-subspace alignment codes that can be used both for PIR and SDMM. So there are these interference alignment that has to happen when you want to decode your file and put the noise all in the same bucket, as Okko was explaining in his lightning talk. So then we have been trying to generalize this with Okko and Dave, or I would say Okko and Dave. I've been mainly trying to keep along. Using algebraic geometry codes when you get a bit more flexibility for the field size, and you can have schemes in cases, parameter regimes where you wouldn't otherwise. Then we worked on quantum PIR together with Matteo, Lucas, Tefiol, and a Japanese group, and then Sides group very recently. Some references, and then I join Olgitsa, thanking all the crazy cat ladies and everybody else for this talk, and happy Women's Day. And then I had some spare slides if I didn't run out of time, but I think I did. So thank you very much.
Thank you.
I know it was on your last slide and you didn't have time to talk. Can you give us a hint about quantum private information retrieval?
Yes, so there you get to use these weekly self-dual codes. You basically combine again our star product scheme, so you can utilize very much what we had already done. And then Masahito and his student had been working on quantum PIR when there's no coding. So then taking there to some protocol and some other schemes. It depends. We have a bit different style constructions, but one is very much following this star product scheme. And then by the quantum, what actually happens is that essentially, well, it's not very surprising. You can double your rate. So when you do replication, you can get privacy for free, so to say, if you do quantum. And by quantum, I just mean that I have a quantum communication step, no quantum storage or messages, just like, classical storage and then quantum communication. So you send qubits instead of finite field vectors.
Has the model also been considered where the adversarial, service or whatever might send you back like incorrect linear, like?
Yes. Yeah. So there's some few works on that, and one that follows our star product thing is this. Well, it exists.
So your model, I figure it was sort of generalized, right?
Yeah. Yes, exactly.
It's just decoding from here instead of the read.
Yes. Yeah. You stack your error that you choose, and then the error part that is given by the channel or adversary, and you make sure they don't overlap. And yeah.
All right, if not, thank you very much, Camilla.